Hello students, hello, welcome to today's session. Today we shall be discussing one important topic of hydrolysis of cyanides and isocyanates. This particular topic belongs to nitrogen containing compounds, which I have seen that most of the time students are a little weak in this particular topic because this is the last part of organic chemistry. So in this particular topic, I shall be discussing one question sent by someone, a beautiful question through which we will see into the insight into the hydrolysis of cyanides and isocyanates. First, see the question, pause the video and try to solve it out, and thereafter see into the discussion. So I hope you people have tried this question by pausing the video. This is again a very important question, as it is very evident here that the examiner is talking about the hydrolysis, basic or acidic hydrolysis of cyanides and isocyanates. So first let me give you a little insight into the topic, and thereafter we will see that how is it very interesting in evaluating that how this is very interesting in regard to the addition reaction. So now see here. Now if I talk of this particular alkene, into this if I add water, so we know that this OH goes here, H goes here. So in, as a matter of fact, what we are able to see that across the double bond, when you add water on waters, one of the hydrogen of water goes to one carbon and OH goes to the next carbon. And if you take into account the why this has happened that way, because the H positive is going to attack this one, and these two electrons go here, and this results in the formation of carbocation. And once this carbocation has been formed, then water is going to attack with its lone pair. This is the viewpoint, or this is the mechanistic viewpoint by which this reaction might have happened. So here comes the protonated alcohol, and this is the positive, and lastly what happens is this H positive goes out, as we have already discussed number of times. When H positive is added at the first step, it has to come out at the last step. So this is what you have got. So this addition reaction has happened in such a way that one of the part of the reagent goes to this carbon and second part goes to this one. Now it would be somewhat different in isocyanates. Let me give you one more example. Say for example you have this given aldehyde, into this you do the addition of water, which would happen at equilibrium because the product formation is little less. But as a matter of fact, if I happen to explain it to you, this H would go here and the OH would go here. Why is it so? Because this is having a lone pair. This is first attacked by H positive. As a consequence, first this sort of moiety is being formed, and then this moves here. Basically, when slight amount of acid is added to aldehyde or ketone, it increases the positive charge on carbonyl carbon, which earlier was delta positive delta negative. Now it would get a clear cut positive charge. Now once it got a clear cut positive charge, then water's lone pair again attacks it, and finally would happen, I am writing it with with deleting one step. So one, first the water goes onto the carbocation, and then the loss of H positive, and finally you end up with what exactly has happened. On one side you would end up getting this what you call it as this H, and on other side it becomes OH. So what basically you are able to see in this particular case, that on this there is a double bond here, carbon oxygen double bond is being omitted, H gone to one part and OH gone to the other part. So across the double bond, if you do the addition, what I'm trying to figure it out is this one, that what I just wanted to say among these two, or the next one also, that wherever you have double bond in the sense like this, or in the like this, or like this, you have double or triple bond of this type, and if you happen to do add some reagent into it, so the reagent goes to like this, A goes here, B goes here, or A goes here, B goes here, or A goes here, B goes here. And now that would depend what is A and B. In this case, B was your, that would depend how you are going to add it into it. Now similarly, if I do one more for you, which is quite interesting to show it to you, that if you add into cyanide, if H water is being added, again the viewpoint would be the similar one. This lone pair first attack the H positive, just like in the case of aldehyde. So you end up getting this positive charge, then this moves here so that this carbonyl carbon or cyanide carbon would get a clear cut positive charge. So this would get a positive charge, and lastly you add water into it followed by deprotonation. So water goes here and you end up getting, with loss of one H positive, here comes the OH double bond NH, and this may undergo tautomerism to give you RC double bond NH2. So basically when you add 1 mole of water to cyanide, it basically gives you amide, which is a part of which is a part of partial hydrolysis. And further addition of water may also give you acid along with carboxylic acid along with evolution of ammonia gas. Now how is it different in case of isocyanate? This is beautiful to tell you that in case of isocyanate, if I add the simple narration like this, the one which we have done already, first we have to understand about the bonding of it. So the bonding is here is somewhat like this. The carbon is having how many electrons? Carbon is having 4 electrons, 1 2 3 4, and nitrogen is having 1 2 3, and this one is the fourth electron. And where comes the fifth is this one. So basically this is positive, this is negative. I mean to say, what exactly I want to show it to you in another way of writing it is isocyanate has a this sort of a viewpoint, or you may also write it like this, that there is a one coordinate bond. So these two electrons are of nitrogen in this shared pair of electron. So this basically, either you take this one or this one, basically you are able to see that in isocyanides there is a development of negative and positive charge already. Now into this, if you add water, the things would be somewhat different. So this is very important to tell you. Let me place it once more for you. As I said, isocyanates has a, I may say here, isocyanates react differently when they are undergoing addition reaction. Addition reaction happens to take place somewhat differently as compared to other other function group, which is other function groups which are having double or triple bond. Now see what I'm saying it, that what you are able to see is, first if in case I add E positive, that is electrophile, this goes here, so it results in the formation of this, and a positive, this N would have positive charge, this carbon becomes carbon got attached with the E. Now what would be the next step? Next step is would be the nucleophile. Now here I may ask you where the nucleophile would attack. Generally people say it would attack here, but this is not possible because nitrogen's octet is already complete. Nitrogen's octet is complete, so it has no tendency to gain electron because it cannot make it cannot extend its bonding that way. So the point is that how does it would happen then? So it would happen in this form. This nucleophile would attack, this is very interesting, on this carbon, and this moves here. As a consequence, what is being generated is N double bond C E and nucleophile. This is beautiful. What I am trying to convey to you, that isocyanides are the class of compounds. Isocyanides are the class of compounds where electrophile and nucleophile add across same carbon. This is very important. Unlike the case of alkenes, alkynes, cyanides, or aldehydes and ketones, where reagents one part add across to one atom, and the one which is added to the next part is either electrophile or nucleophile depending on the type of reaction. Now what we have concluded, that in isocyanates electrophile and nucleophile add across same carbon. This is very important. Now let us see how the water would have attacked it. So here in this case, what would be the fate of water? So first you added H positive. So H positive have attacked this. So it resulted in the formation of this one. This is very interesting. And now what would happen? Where would the water would attack? Lone pair of water would attack this carbon rather than this nitrogen. And this goes like this. So as a consequence, most of these steps would be at equilibrium, and this would give you H, and on this side you would get water. and the one H positive you added, that goes gone out in the form of H positive here, and you end up getting this species. Now, if you could see this carefully, this particular species which we have written is nothing but, if you tautomerize it, it would reach to this point. Let me show it to you once again what I'm doing it here. So let me place this molecule here. So what I'm saying is that this molecule is N double bond C, R N double bond C. On one side this is OH and this is. Now this is what I'm saying is tautomerism. This H gone here, this bond goes here, this goes here. So the H positive takes this position. So this is what you call it as an alkyl formamide. So this again could add water into it. So what very important here is that in isocyanides, the electrophile and nucleophile, the H positive of water and OH negative of water add across to the same carbon. So we may say here that in the case of isocyanides, the water's H positive and OH negative added across to the same carbon. This is very important to tell you. This is the different viewpoint in the case of isocyanate. And another thing, when you happen to do basic hydrolysis of this, that won't happen in isocyanate. If I have water and into this you have catalytic amount of base, this hydrolysis would not happen because this OH negative cannot attack the negative part because there would be negative repulsions. And same is the viewpoint, this OH negative can also not attack this nitrogen because octet of nitrogen is complete. Nitrogen is complete. So it has no tendency to gain that electron. It cannot make 5 bonds around it. So we shall be saying that the basic hydrolysis won't happen. Basic hydrolysis is not possible for what? Isocyanates would not undergo basic hydrolysis. Is not possible for basic hydrolysis. Now we can say here that RNH, this is the alkyl formamide we have already formed, and now if it further undergoes hydrolysis, what shall we be getting? So we shall be getting along with that primary amine. This is going to give you primary amine along with the molecule of formic acid, So now how to figure it out that how this reaction might have happened? So first you can say this is the lone pair which is being attacked by the H positive. Why is it so? Because this lone pair, if can move here, this would intensify the negative charge on carbonyl oxygen, which is more basic in the sense that it can attack this H positive, resulting in the formation of this sort of a species. So what we shall be getting here is this is positive, and along with it you would get this sort of a moiety. So what we shall be writing it here is positive, this is H, this is OH we have generated. Now what can next be happening? This water is going to attack it, and as a consequence of that, this attack of water would result in the formation of NHCOH positive, and here you would get OH. Now the last step can be this H positive, then because this is having a lone pair, this is intramolecular proton exchange, resulting in the formation of RNH2 positive along with OH, H, OH. Now last step can be shown it like this H positive, the one which we have attacked, gone out, this bond goes here and this lose the system. So what goes out is one, the H positive, and you left with the primary amine along with the molecule of formic acid. So this is very important to tell you that now we can conclude it here. This is very important to tell you that isocyanides on acidic hydrolysis first gave you N-alkyl formamide, which on further hydrolysis would give you primary amine along with the formic acid. So first step may be said as partial hydrolysis, and the second step can be said as, if I completely take it from this side to this side, we can say it as to be complete hydrolysis. So most of the time we happen to do the complete hydrolysis, but if in the process the examiner which is placing this question, if this is formed in between during any reaction, and some reaction is to be done from this side, then you have to take the partial. Otherwise we generally would take the complete hydrolysis. Now this again is a short type of equation which may be asked, or which can be placed in your upcoming exams, that any nitrogen containing compound, if you have some nitrogen containing compound, if any nitrogen containing compound on hydrolysis gives a molecule of formic acid, and what type of hydrolysis, better I would say acidic hydrolysis, it may have NC group in it. NC group is also said as carbylamine group. So if in case on the hydrolysis of a nitrogen containing compound you end up getting formic acid, which can be reduced with Fehling solution, which can be reduced, here it is being written, so that particular species is nothing but the starting material must have some NC group or carbylamine group. Now moving on to the next part where we have to talk of cyanides. This cyanides hydrolysis in acidic medium, the mechanism is already been defined by me few minutes back. So this is the amide formation, and this amide on further hydrolysis gives you formic acid, carboxylic acid along with ammonium salt. Because I may say first ammonia is being formed, but since the system is acidic, it would form ammonium salt. Now, what about the basic hydrolysis of cyanides? In the case of basic hydrolysis, this is delta positive, this is delta negative. This OH negative attacks this and resulting in the formation of this sort of a species. So this is nucleophilic addition, and this would get a negative charge. Now, once this get a negative charge, then this abstract H positive from the water. H positive from the water. So this results in the formation of this sort of a species, and along with it what goes out is OH negative. This OH negative which we have started with has gone out. That is what you call it as catalytic hydrolysis in the basic medium. Now this particular species may undergo tautomerism to give you the same amide which we have already written in the acidic hydrolysis also. So this amide is being generated again as we did for the acidic. In the basic hydrolysis also you end up getting the same amide, and this amide, if we do the further hydrolysis of it in the basic medium again this OH negative would place it here, this goes here, so resulting in, if I do it in SPD way, this would get something like this. Although this is not a very favorable step, but a good amount of refluxing for a longer duration of time is required so that it can throw out this amide, which is a bad leaving group as compared to. So this would result in the formation of carboxylic acid. Now what is the driving force? Because this amide is not a very good leaving group. Now this would be nearly irreversible. Once this amide is being formed, this amide snatches out the H positive of the carboxylic acid generated. Once it is being generated, and this results in the formation of ammonia, which is a gas which leaves the reaction mixture, resulting the reaction to be driven to the forward side. So the last equilibrium step is almost irreversible. So that drives this reaction from this side to this side. This is very interesting to tell you. So we can conclude here is that if I talk of cyanides, cyanides has happened, is undergoing acidic hydrolysis as well as basic hydrolysis. So both hydrolysis are possible. So if you added 1 mole of water, first they would give amide. This also would give amide. And if further hydrolysis is being done, it would lead to the formation of another mole of water would lead to the formation of carboxylic acid with ammonium salt, and in this case in the basic medium it would result in the formation of carboxylate ion along with the ammonium gas. This is very important, and this part is partial hydrolysis. And if I go again, many students generally would ask me that if 1 mole of water is being placed, will we have to do the acidic the partial hydrolysis or complete hydrolysis? That again would depend if during that particular question this amide which is being formed is further used somewhere. If it is the next step related to that particular question is driven from the amide, then that one water molecule of the species added to the cyanide would lead to the amide formation. And if it is not shown in that particular question, then you have to actually take it to the carboxylic acid or to the salt formation. So this is very important. Now let us check what the options are there. So we have understood many things about this. Basically, the isocyanides addition is somewhat different from the other unsaturated compounds or function groups undergoing addition reaction. So first step, let us check what is to be done in all of these questions. So first question is that phenyl isocyanate undergo basic hydrolysis. This is categorically rejected because this cannot attack here nor it can attack here. So this is not possible. So this statement in itself is wrong. Methyl isocyanate on acidic hydrolysis gives you primary amine acetic acid. Methyl, so they have given methyl isocyanide. So methyl isocyanide is to be placed here. So methyl isocyanide on acidic hydrolysis will give you acetic acid along with ammonium salt. So they have shown primary amine. This is a wrong statement. Although it is acetic acid is being formed, but methylamine is primary amine is not being formed. Phenyl isocyanate. In the case of phenyl isocyanate, H positive of water, H positive of water goes to the nitrogen, which is not possible. Positive positive repel each other, and OH negative goes to the carbon. This is wrong. In fact, H positive and OH negative both goes to the same carbon. So this is wrong. This both would go to the same carbon. That is the beauty of isocyanate. So this also is a wrong. And benzonitrile means phenyl cyanide on hydrolysis can be hydrolyzed in both acidic and basic medium. That is perfectly right. So on acidic hydrolysis, this would lead to benzoic acid along with the formation of ammonium salt, and on the basic hydrolysis, it would lead to the benzoate along with the formation of ammonium gas. And here we lastly I would conclude it that isocyanide would not undergo basic hydrolysis, rather it would go acidic hydrolysis, whereas cyanide would undergo both acidic and basic hydrolysis. So this is an interesting question, and I hope you have understood the whole of this particular discussion. Thanks a lot. Do subscribe to my channel if you have not yet subscribed to, so that you could get the notification at the earliest. Thanks a lot. Have a nice day. Stay safe. Take good care of yourself.